All right. We're going to just review these states of matter. We're going to talk about the whole slideshow real quick. I'll put it in the Google Classroom. You guys have all seen that, this little PowerPoint. So that's it. So 3 big states of matter. You normally deal with are solid, liquid, and gas, even though most of the stuff in the universe is plasma. Solids have a specific shape, like a cube of ice, and the properties of the solids are due to the arrangement and the shape. Now, this is a solid, and these little sticks here, they stand for the chemical bonds that hold these molecules together, all right? And we have to break these sticks. We have to break these chemical bonds if it's going to be a liquid, all right? Now, if you add some thermal energy or heat, see, thermal energy is like a new way to put it. If you add some thermal energy or heat to a solid, you're going to get a liquid, all right? And the amount of heat that you need to apply is called the heat of fusion or the heat of melting, okay? And depending on how much of a solid you have, the heat of fusion is the amount of energy it takes to bring that solid up to what's called its melting point. Okay? So, a liquid is something that has been given enough energy that the bonds between the atoms still exist, but the bonds aren't strong enough to hold the atoms or molecules in place. So they can move around, but they still can't quite let go of each other. That's a liquid. All right, and melting point, that's a 4th grade term, right? The melting point of water is 0 degrees Celsius. All right, now let's take a look at this question. These are the types of questions that you're answered, that you're asked. Which best compares how the bond strengths affect the physical properties of iron and lead, okay? Now we're going to look at this. You can make a guess, okay? If you're at home, you can pause this video and try to make a guess. What do you think is going to affect the melting point? The chemical bonds, what do you think the chemical bonds are going to affect? The melting point or the density? What have we been talking about? Have we been talking about density? No. So the stronger these bonds are, right here, the higher the melting point. Does that make sense? So when you look at a question like this, you've already narrowed it down to A or B. And it says, A says iron has a higher melting point because the bonds are stronger. And that's it. B doesn't make any sense. If the bonds in iron were weaker, the melting point would be lower, correct? And lead is a metal with a pretty low melting point. The only thing I don't like about this question is you don't know anything about iron and lead, so you don't even know if iron has a higher melting point than lead. Does that make sense? They're assuming that you have a chart or something you can look at that you know. Okay. Now, a liquid doesn't keep its shape. It takes the shape of the bottom of the container. Okay? And then this is how liquids move. They're trading places with each other, but they're not going away because they're still pulling on each other. Every time they hit, they pull on each other, kind of like taffy. Okay, now if you add energy to a liquid, you will get what's the state of matter higher than liquid? Gas. So if you add energy to a liquid, you'll get a gas. Gases take the shape of the container and they also fill the container. And the amount of energy needed is called the heat of vaporization. Okay? The heat of vaporization brings you to the boiling point. Okay? There's 2 ways to turn a liquid to a gas. One is boiling, the other is evaporating. Evaporation is something that just occurs at the surface of a liquid. When you're cooking, you're boiling the water. All right? Boiling the water means you bring the entire body of water up to the boiling point. Evaporating the water is very simple. Little bits of sunlight, little photons of light can just hit a couple of molecules just on the surface and barely give them enough energy to turn into a gas and they go away. Okay, this is how gases move. You notice that when they collide with each other, all the energy is conserved. Gases have a lot of kinetic energy. And their collisions we consider to be elastic. Then now we're down to solid, frozen in place, literally frozen in place. Liquid, we're trading places with each other, but we're still pulling on each other. And gas. Gases don't care anything about each other. And that's that. That's the end of that little flip. That review.